Hello everyone. Today I'm going to talk about a paper on understanding task transfer in vision language models. Current VLMs have achieved great performance on a wide variety of tasks. However, they still fall short compared to human performance on perception tasks like counting, spatial reasoning, and relative depth. Very often, they are fine tuned on task specific data to get good performance on that task. But what happens to other tasks? If you fine tune on-set depth, what happens to counting? What happens to spatial reasoning? We surprisingly don't know how these tasks interact with each other. There might be correlations which may be beneficial, or there would be negative interferences. In this paper, we aim to study this behavior. More precisely, we aim to figure out how does fine-tuning on one perception task affect zero-shot performance on other perception tasks. For this setup, we use a pre-trained VLM and perform LoRa fine-tuning for a task. We then evaluate this fine-tuned model on all the tasks that we have. We then repeat this over all the tasks in our suite. For our setup, we use the Blink benchmark, which has a wide variety of perception tasks. We create training datasets for each of those tasks using their original methodology and then evaluate the fine-tuned model on the whole benchmark. The model that we use is Qwen 2.5 VL across different model scales, ranging from 3 billion up to 32 billion, with each fine-tuning being done across 4 different seeds to rule out any random artifact. Using this experimental setup, we aim to achieve a task transfer matrix, where the rows are fine-tuned models on source tasks and the columns are the target tasks. The cell values represent the transferability score. A positive score means it improves the task, and a negative score means it deteriorates the task. Using this transferability score, we can define task transferability. Essentially, aggregation of the positive transferability scores in a row is called positive task transferability. This gives a general sense of how much that task transfers to all the target tasks. Similarly, we can define negative task transferability. In similar lines, we also define malleability. So the aggregation of transferability scores in a column can be called the task malleability. It helps us measure how sensitive a target task is to fine-tuning on other tasks. A high value would mean it benefits a lot from them, and a low value would indicate deterioration from other tasks. So this setup helps us to several inferences and key takeaways, which I will now touch upon. So firstly, we find that positive transferability and malleability increases with model size. So as we go from a 3 billion model to a 32 billion model, all the positive trends and task relations we see become stronger as the model size increases. Surprisingly, we find no such trend for negative transferability. We look into trends based on task categorization as well. So the benchmark provides task categorization into low, mid, and high level tasks. We find that low level tasks are highly positively transferable as well as highly positively malleable. So this means that by fine-tuning on low level tasks, most tasks gets improved. However, the inverse is also true. If you fine-tune on most tasks, it leads to the improvement of low level tasks. We also find certain task characteristics which we call as task personas. So these summarize how the tasks behave in the transfer ecosystem. For example, donor task, as the name suggests, helps the most to other tasks and have highest positive transferability. Its counterpart, pirate tasks, deteriorate other tasks and have high negative transferability. In similar lines, sponges have high positive malleability and seas have high negative malleability, and they can help or degrade the other tasks. So you might ask where all this analysis is helpful. We believe it has several practical applications ranging from dataset curation, learning paradigms, and benchmark design. We demonstrate one such application for dataset selection. We find that when we create data mixtures from the previous analysis that we showed, it can even outperform direct fine-tuning on the target task that we want. So this leads to more efficient paradigms of dataset creation. To summarize, we present a systematic study on a broad suite of perception tasks We introduce a new metric to compare the task transfer, as well as present a downstream application for better dataset selection. We hope this analysis would be helpful for future practitioners. Thank you.